I like the one we just used, but let's try the other one, okay? Let's just try the other one. The other one was the derivative of the unit tangent vector magnitude over the derivative of the position vector magnitude, right? All right, so I'm going to need to find the derivative. What's the derivative here? Ooh, nice. 1, 1, 2t. I need the magnitude of this. What's the magnitude of this? Square root 1 plus 1 plus 4t squared. What is capital T of t? What's capital T of t? Not this, but what's capital T of t from last class? It's this divided by its own magnitude, right? And this right here is a number, isn't it? And so I just divide each of these components by this. So watch, I get 1 divided by this root 2 plus 4t squared, and then I have 1 divided by root 2 plus 4t squared again, and then finally 2t divided by root 2 plus 4t squared. Ooh. That's my unit tangent vector, isn't it? But I don't want that. I want its derivative's length. Do you want to take derivative of that? That's going to suck. Do you agree? And even after I'm done taking derivative, then I have to find the length, which is the square root of each of those components squared. That's really going to suck, isn't it? Which is why I'm going to lean towards the other formula now. And that's what would indicate to you to lean towards the other formula also, is when that looks really bad. Now, like I said, sometimes this is easier. Sometimes, you know, you get here and you take the derivative and you get numbers and everything's just super clean. But when that doesn't happen, the other formula is probably more useful. So on the other formula, do we need these two? Yes, but instead of this, we use the second derivative also, right? So let me get my second derivative in here. Is my second derivative nice? Oh, yeah. 0, 0, 2. And I'm supposed to cross these two together, right? I'm using that formula again. What would r prime t crossed with r double prime t be? Let's see. I'm doing these two crossed, right? So cover this up. What do we have there? 2. Cover the middle up. 2, 0, but then subtract, so negative 2. And finally, cover up these two, 0. What am I supposed to do with that in the formula? Find its magnitude. So what's the magnitude of this? Square root of 8, right? 4 plus 4. So
Shouldn't it just be 2, 2, 0? 2 minus 0.
2, what?
For your components.
Where?
For your j.
Covered up these. Should be 0, 0. Is that what you're talking about? For j, the middle one? Oh, the middle one. That's 2, and then that's 0. But because j, remember, you always subtract. We good? We're not done, right? So the curvature, I'll just cheat and I'll use this formula. The curvature is this. That's it, right? We know this is what? Root 8 over, and then the derivative. Is this the derivative right here? The magnitude is derivative, right? cubed. This cubed. So it'd just be square root of 2 plus 4t squared cubed. That's it. So do you see for this curve, the curvature actually depends on t, right? Depends on where you are on the curve. As t gets bigger, what's going to happen to this curvature? As t gets bigger, the bottom gets bigger, the curvature gets smaller. And that's what was happening in that spiral. This is that spiral, by the way. So as time went on, the curvature got smaller. When time was very small, the curvature got bigger. All right, I hope that illustrates the importance, I guess, of knowing when to use which one. When you do your homework on curvature, just realize both of them are there. And I have an updated homework assignment. This is the updated homework assignment. What I've changed in here is I think I took out number 12, I added number 7, and then 13 through 16, I think I had only asked you to compute capital T in the previous homework assignment. And I said, but if you read the instructions, it asks you to calculate capital N. And I haven't told you what that is, and I'm not going to tell you what that is. I want you to go in there and read the book. There's a formula for this. It's not that much crazier. But I want you to on your own, read through the book and figure out what this is. And then try and see if you can determine what the geometric relationship is between these two vectors. This is the unit tangent vector. This is the unit normal vector. Geometrically, how are they connected? So see if you can figure that out on your own, reading through the book. And I think that's it. What do you think? I still have 10 minutes. Sorry, I still have 10 minutes. I don't want you to feel like you're not getting your money's worth here, all right? 10 minutes is something I'll beg for later. I'm going to introduce you to the next section without getting into too much detail. It's very visual. So visual, in fact, that can somebody, can you kill a few lights? Just, yeah, that's good. I don't know how that's going to come out on camera, but let's try it. Okay, we're moving into a new chapter now. Okay, a new chapter in the book, chapter 11. There are 13 chapters in this book, right? Our plan is to cover 10, 11, 12, and 13. Finish the book. That's my plan. We'll get to the last page and be done. Close the book, all right? So 11.1, functions of several variables. Okay, we have seen already that anytime we have an equation that has x, y, and z in it in three-dimensional space, we could get like these quadratic surfaces, right? These ellipsoids and spheres and hyperboloids, all these different things, right? But if you can take that equation and you can solve it for one of the variables, like z, so you get z on one side of the equation, then essentially you've got, let me blow this up. If you solve for z, then the other side of the equation just has x's and y's, then we can say that z is basically a function of x and y. Instead of like we used to say in college algebra that y is some function of x, right? When we had something like y equals x squared plus 2x plus 1. So you give me an x, I spit out a y, right? Here, if I get z by itself and the other side is x's and y's, then you have to give me an x and a y, and I can spit out a z. Understand? Remember, one input, one output is what we needed to have a function, right? One input, one output. With this sort of notation in mind, this notation, z is some function of x comma y, the input, since I have to give you an x and a y to determine z, the input can be looked at as being a point living in two-dimensional space. The output is a single number, and it can be looked at as being just a number on a number line. So that means you need 2 dimensions for the input, 1 dimension for the output. So we will be able to visualize this picture in 3-dimensional space. I'm jumping ahead here. So this is a picture. This is a picture of what I'm talking about. You have the input, right? So you have to pick an x and a y somewhere in its 2-dimensional space. And then it spits out a number over here, right? That's our z. But I can visualize all of that in 3-dimensional space. If I look at the ground as being the input, and the z coming up, the height of the point as being the output. So as I move around, if I pick different points, do y'all see that I'm moving around the top of that surface up there? Do y'all see it up there? Okay. So for every point in the domain, we have an output up here. Here's an example, our first example, of a function of 2 variables, x and y. Here it is. See? You give me some x's, you give me some y's, you can spit out a number, can't you? First question, what's f of 2, 1? That means replace x with 2 and y with 1. And it matters, the order matters here, right? 2 is x, y is 1. So what would this be? Square root of 2 plus 1 over 2 minus 3, right? Which is root 4 over negative 1, so negative 2, right? So we plug in a point, it spits out a number. Let's try another one. F of 0, 0. What do you get? On top you get root 1, don't you? Which is just 1. On the bottom you get negative 3. And so this is just negative 1/3. It's pretty clean, pretty straightforward so far. All right. What about this one? Square root of negative 4 plus 1 over negative 4 minus 3. Uh-oh. This is square root of negative 2 over negative 7, isn't it? And you can't do the square root of negative 2. Not unless you're willing to come in and bring imaginary numbers in, which we're not. So that means that this point cannot be plugged in, right? Which means there is some restriction on my domain. The question is now, what is the domain? And I have enough time to show us. What is the domain? So let's talk about it. What are we afraid will happen with this function? What are some things? Just look at it up there algebraically. What are some things that you want to avoid? What's that? Sorry. What negative 3? What? Positive 3? What do y'all think?
If x is positive 3, you
okay, we don't want x to be 3, right? We don't want x to be 3. So we have this so far. This cannot be true, right? That bottom cannot be 0, which means that x cannot be equal to 3. Agreed? That's one thing. What's the other thing we don't want? Or you can say it the other way. What do we want? We don't want a negative under the square root, right? So I've got to make sure that x plus y plus 1 is never negative. So greater than or equal to 0. That's what I want, right? What the hell is that? Oh, this is a linear inequality in 2 variables. I actually went over this when I subbed that class the other day for Math 1324, which is Business Math 1. This is just Just move everything over, right? And you get this. If I were to say that's an equal sign, if I were, then that's a line, isn't it? But if I say this, then it's no longer a line. What is it? It's a shaded portion of the plane. So let me try in the last 3 minutes. I'm going to have enough time to get some idea of what's going on here. Okay, first of all, this is my domain, right? Remember we just said the domain is in two-dimensional space. I cannot have x equal 3, right? Remember, this is x, this is y. So what does x not being equal to 3 mean? What's that? S. That's right. At 3 here on the x-axis, of course I can't have that point, but I can't have any x values of 3. So this entire vertical line is pulled out of any possibility. Yeah? Then it's okay to have this line, right? If I make that an equals, it's okay to have that. Let's graph that. It would have a y-intercept of -1 and a slope. So it would be like this. Y-intercept of -1. It would go here and have a slope of -1. So it would go something like this. And it would, of course, not go through there. And then go this way. So that line is okay to have, yes? Now, which side of the line is also okay to have? It's either going to be the top side or the bottom side. How do you check? You can just plug in any point and test it. So let's just test this point right here. That point's good because it's the origin. Does 0, 0 work in this inequality? Yes. 0, 0, 1 is bigger than 0. That works. That means everything on that side of the line works. This is the domain, everyone. It's actually part of two-dimensional space, and the only way to really see it is to graph it. So that means that if I go now and I graph this function and I look on the ground, that stuff is not, this stuff right here, above that is the only place I have picture. I'm going to show you the graph and then you may go. I forgot to pass out the sign-in sheet, but that's all right, because I gave back your test today. Here's the graph. Look, this is the graph of that function, everyone. That's the surface. It's weird, right? See it? Isn't that weird looking? It's doing some weird stuff. Watch this. I'm going to look at it from the top. Straight down. Do y'all see it? If I look at it from the top down, it's this. What I just drew. It's that line at 3 taken out. It's this line and everything that way. Okay. We pick up where we left off next week. Your mini exam is due on Monday, right? Yes. So, y'all have a good weekend. Can someone hit the lights, please? Thank you.